Hello everyone. I'm Vincent Reverdy, and I'm very happy to be able to talk about multidimensional arrays today and to talk about fancy C++. The project I will describe has been the result of many collaborations, and I will try to give an overview of what we have done to simplify and to maybe give a direction on how we may implement linear algebra in C++. So this talk will be about linear algebra, will be about templates, will be about C++20, about writing language within language, all fun stuff. So I will first give a small introduction on the topic. I will try to be brief. Then I will speak about the current standardization effort on linear algebra that is going on in C++. And then I will try to talk about possible directions for the work that is being done, and how we could have both at the same time high performance and things that are very easy to write. And then I will dig down into very detailed problems, and there will be quite a lot of code and quite a lot of technical code, but I hope everything will go well. So, starting with the introduction, I guess that if you're here, you are interested by multidimensional arrays and linear algebra in a broader sense. And as linear algebra is basically everywhere into computer programming, I think it's not surprising that we may need in code like 1D arrays, 2D arrays, and 3D arrays. 1D arrays are sometimes called vectors, even though vectors in mathematics may be kind of a different object, because a 1D thing, a 1D array can represent an array of coordinates, while a vector in mathematics have to ensure that certain constraints are verified when you change, for example, the base. And same thing for tensors. Tensors are used in programming to talk about multidimensional arrays, while in mathematics they refer to a very specific type of object with certain properties. So that being said, in the rest of the talk, I will talk about multidimensional arrays, and I will not dig into these problems of vocabulary. So we have these objects, and these objects are used in many, many different areas. One of them, for example, is video games. When you want to implement anything that has to do with graphics or anything that has to do with a physics engine, that may be very useful to have vectors and matrices, or at least multidimensional arrays. The one other area where linear algebra can be very useful is science. And on my side, I am working in astrophysics and in mathematics, and I'm trying to use a set of algorithms called optimal transport in order to see how we can guess the initial conditions to form, like we take cosmological simulations of formation of galaxies, of galaxy formations, and then we try to use computational optimal transport to see where they were before in time. And if that works, then that gives us insights when we will apply them to real data to understand what has been going on in the past. And to do that, contrary to video games, where the most needed are generally very small arrays and you need to have a lot of them and have them very fast, in my case, I may have up to 6-dimensional dynamic arrays with billions of elements. So even though the constraints are a little bit different than for video games, all of that are kind of the same thing in mathematics, basically vectors, matrices, and how do we operate with them as fast as possible. So linear algebra, as you know, is everywhere. We could find many other examples, and I will stop the introduction here because I don't think it's necessary to highlight why it's useful to do that. So that being said, in C++20, we still don't have a standard way in the standard library to deal with multidimensional arrays. A stud matrix is a long-term goal that we may have, but for now, even though a lot of other languages have that, we don't have it in C++. However, there has been, over the last few years, quite a lot of effort done in that direction. One item of this effort has been the work on MD-span and related things. So MD-span is a non-owning multidimensional array reference. Let's say you have a block of memory, a linear block of memory, and you are interested in seeing that block of memory as a multidimensional thing. So that the functionality MD-span is trying to provide. And related to this proposal, there has been MD array proposed recently that kind of extend that to deal with memory allocation and everything. So that's one thing, and that's probably the most advanced proposal so far in that direction. Another thing is our papers on linear algebra in general. So the committee has been reviewing papers about what would be needed by the community, what is needed by application, and there has been a proposal that tried to focus on a higher level view of things. The long-term goal being to be able to have a standard matrix in the C++ standard, as in the vast majority of other programming languages. Another effort has been also quite recent, trying to bring the BLAS, the basic linear algebra subprograms, which are very efficient routines to do linear algebra operation, to the C++. These routines have been tested and optimized for years, and we still don't have ways to deal with them in C++. So there has been investigation in that direction. And finally, there has been also some papers on different requirements, or some trying to investigate the proper vocabulary to use for these objects in order to standardize something that would be reliable and solid, as we like to do in C++. MD-span is for now the name that is used. However, several competing names were given, like psi array, numeric array, VLA array, multidimensional array, multi-dim array, MD array, which is the pattern MD that has been kept for now, and multi-array. The problem with multi-array is that we have already multi-set and multi-map in C++, and in that context, multi means a different thing. Some alternatives to that about how to name these objects would be to use ND, as it exists already in Python. And this would make sense because these objects are, in practice, n-dimensional objects, and n, in that case, is finite and is known at compile time. And this is how these objects are sometimes called in math. The other approach would be to name the things hyperarray, or with an underscore note, because when we generalize things in higher dimensional space in mathematics, we sometimes use the hyper prefix to call the result. Like we have hypercubes, hyperspheres, and higher dimensional matrices are sometimes called hypermetrics. But for now, the current proposal has taken MD array. But this might change before standardization. I personally would prefer that it would change, but we'll see. So that being said, handling linear algebra in C++ is a very long-term and very complicated task. And what the committee has been, the approach that has been investigated by the committee is a standardization by layer. By standardizing first the most simple pieces and then building stuff on top of it. So we would start by non-owning reference to arrays like mdspan. Then there would be a brick of the BLAS, for example, with basic algorithm and operation. On top of that, we could build owning arrays dealing with all the problems of memory allocation. Then on top of that, we could have a library of overloaded operators so that one could write my matrix 1 times my matrix 2, and the operator times would do the right thing, the right type of project. And on top of that, in the long term, we could even add geometric aspects to deal with vectors and spaces and stuff like this. But this talk will focus on the first layer and see how we can make that, how we can try to make that as simple, powerful, and as possible using C++20. But before going further, we need to take a look at what is currently in this proposal to see what are the different types of objects, how they interact between each other, how the things are specified, to understand what the mdspan is. How do we look to a zone of memory and interpret that as a multidimensional thing? So the first thing the proposal describes is a template class called extents, and it takes as a variadic list of template parameter, list of integers. Then there are layouts to specify, layout mapping policies to specify how the dimensions are, when the user write code, how the subscript operator is mapped to the internal memory representation, dealing with row major or column major problems, for example. Then there is accessors that describe how to access in practice an element of memory or a group of elements in memory. And then the other thing, the last thing, is a basic mdspan that groups all these elements together with an element type, for example, double, int, or whatever, then the extents to specify the shape, the layout policy, and the accessor policy. And for simple use cases, the basic mdspan is renamed mdspan when the only thing that matters is the type element and the shape of the thing. As a remark, you can ask questions during the talk, and at the end of each part, I will answer them. So don't hesitate to ask questions, and I will process them at the end of each part of the talk. So that being said, if we look closer to what an extent class is, so as I said before, it takes a list of integers as a varied list of integers as a template parameter. It defines different constructors. Some of them, nothing very surprising here. Some of them may construct an extent from another extent with different parameters. There is assignment, an assignment operator, but nothing very surprising here. And then there are different types of observers. There is an observer to get the rank, the number of dimensions the multidimensional array will have. And because these ranks can be either static, specified at compile time. For example, I want this dimension of my array to be fixed and its value to be 5, or they can be dynamic. In that case, the dimension could be resized during the course of the program. So there is a wrong dynamic function to get what the number of dynamic axes are. And then there is an extent without an S function that takes an index to query the size along a particular axis, along a particular dimension. So for example, if you have an array, a multi-dimensional array with 3 dimensions, extent 0 will return the size along the first axis, extent 1 along the second axis, etc., etc. And finally, there are some exposition-only parts to store the dynamic extents. Then there are the layouts. So layouts are a way to specify the mapping between the dimensions and the way things are stored internally. So layout left is, so we have a layout left, layout right, etc. The layout left declares an internal class called mapping with several constructors and assignment. Nothing surprising here. It takes an extent as to be built, and then it defines ways to access the extent and to access specific things given a set of indices. And then there are ways to query the way things are represented in memory to ask whether things are unique, contiguous, or strided in memory, to have a feeling of how things are stored and how we may operate on them. And the mapping stores the extents it has been given at construction. And using that way of specifying things, it's possible to define all kinds of mapping between the API and the way things are stored in memory. Then there is the accessor. So accessor is it's a very simple class to access things in memory and to access different elements, and so either one element or different elements at the same time. And finally, the empty span that combines all these things together. So it defines a few types. Then it has some constructors that takes a pointer as an input and dynamic extents, or a mapping type, or a pointer, a mapping type, an accessor, etc., etc. Yeah. The only thing to remember here is that it combines all these elements in a multi-dimensional view on things. And there are some assignment operators. Again, nothing surprising here. And operators to access the elements. So there is an operator here to get a reference that takes only one index, and there is an operator that takes several indices to access the elements. And there is also a version that takes an array of indices to access the elements specified by the different indices in the n dimension of the empty span. And finally, still in the same class, there is a way to access the accessor and to access the different internal properties of the empty span. Basically, copying information that are handled by either the extend the layout policy or accessor policy. And I think that's it for the most part. So if we summarize what's interesting and the main contribution to the design proposal has been to define an API to propose MDSpan as the product of an element type, an extent that describes the shape of the multidimensional things we are looking at, a layout policy to specify the mapping, and an accessor policy to specify how individual and contiguous elements can be accessed in memory. And that is a huge effort, like to be able to divide the parameter space in these and to conceptify the parameter space in these 4 things. It has been quite a lot of effort from the authors. And honestly, I find their work really amazing so far. And I'm very excited by what will follow. However, as one of the lowest layer thing, this proposal has some simplification. It is non-owning, meaning that all the problems of declaring memory and to allocating memory are not handled by this. And it's not a problem, but it just means that for an MD array, it will be necessary to design and to see how allocators will interact with the already defined 4 parameters. And it has been designed for contiguous memory storage. For now, there is no multidimensional iterators, and there is no way of basically iterating on these things. So, given the current state of the proposal, the way one may declare an MDSpan is what is shown on the second line of the proposal. So, the MDSpan of the element type, like double, and then the extents, where every dimension can be either a number or dynamic extent. However, dynamic extent is defined as -1, and this may cause problem because this is a very old school way of doing things, and that have some risks. And this syntax is, I must say, pretty heavy. Like when you have 3 dimensions, it's okay, but when you start to have a lot of dimensions and when you have a code that deals with a lot of different types of arrays with different dimensions, specifying things in that way requires a lot of characters to be typed and not very easy to read. And in the early age of the proposal, the team behind the proposal wanted to allow a different way of specifying thing, as proposed by P0332, a proposal called relaxed incomplete multidimensional array type declaration. And if we had that, we could specify things in the more elegant way to describe what dimensions are fixed and what dimensions are dynamic. For now, in C++, only the first one of the 2 is allowed, but the second one, you cannot have alternating fixed and dynamic dimension. The dynamic dimension has to be in the first one. The library evolution working group in the committee was largely in favor of this syntax. However, the evolution working group was against this language change because it had unintended side effects in different areas of the language, and to just allow this functionality by a core language change, this could trigger suddenly a lot of completely unintended problems. Another problem was that was the one of zero-sized array, because it's currently not allowed in standard C and standard C++ to specify 0 as a dimension. However, stud array allows zero-dimensional array by compiling a special case, and it could be for people who do mathematics as a generalization. It would be really nice to have a way to specify that that we are dealing with a zero-dimensional array along one axis. And even if P052 was standardized, we still would have no way of doing that. So that being said, the point of this talk is to focus on how we can specify the shape of my multidimensional arrays in a nice way and a compact way and a way that would be readable and that would be easy to manipulate. The goal is to obtain something that is generic so that we can cover as much as possible of the parameter space. Something that is high performance, both in terms of computing time and memory, and something that is very expressive, that is easy to understand, easy to read, and easy to write in a concise way. So regarding the question, I may take some of them at the end of the talk, but some of the questions that has been asked are, what are the distinction between multidimensional arrays and tensors? So that's a tensor has to ensure that some properties are conserved, while a multidimensional arrays, like a tensor, is fundamentally a geometric object, and we may look at the coordinate of the tensor, the coordinate of the tensor in a particular base is a multidimensional array. Same thing for a vector. A vector, we may look at the coordinates, but the coordinates of the vector is not the vector itself. Why are the completed extents parameter ptr diff t instead of size t? So that's a long debate. If you don't agree, write to the committee. That's a detail of the implementation. Having just IT seems not enough. What if we want to specify alignment? So I didn't write the MDSAN proposal, but I think this is handled by the layout policy. This must be checked because, again, I'm a simple user of MDSAN. I'm not an implementer. Why do we have special extents name for what is basically some kind of array? Because of the thing I explained before, which is the fact that we may want to specify dynamic dimension or static dimension. Question 6: how do you create iterators of the arrays? For now, there is no multidimensional iterators included in the proposal. When traversing question 8, when traversing multidimensional arrays, can you preserve the concept of left, right? I think so. Then when you traverse the multidimensional array, do you foresee using space-filling curve as mechanism for efficiently traversing the array? That would be very interesting. I don't know if that can be currently specified in terms of layout, but once we have multidimensional iterators in the long future, this would definitely be something that could be very interesting to operate on these arrays. For now, it's just MDSPAN are just views on contiguous memory spaces. And I think that's all the question I will take for now. So again, we want a nice way to specify shapes of multidimensional arrays. So we want something generic, performant, and expressive. And the problem is that it's very hard to have have everything at the same time. And in that context, I will define software architecture as the way of balancing and compromising between the generosity, the performance, and the expressivity. So if in that regard, it's interesting to I think this way of looking at things is interesting to understand why C++ still has no standard matrix in 2020. When people focus on only one axis, for example, focusing on expressivity, the problem collapses and it's far easier to solve. And for example, in a high-level language, you don't care that much. You may not care that much about performance or generosity, and this may be hidden in lower layers of your language. Focusing on two axes of the optimization space still lead to a reasonable level of complexity. For example, if you only focus on performance and expressivity and leave the generosity alone by only providing one single type, it's relatively easy to do. But when one wants to address the three axes at the same time, this is what makes the design a real challenge. And in C++ and in the standard library, we are aiming for these three things at the same time. And this is one of the main reasons, I think, that we still have no standard matrix in 2020. Ideally, if everything was possible, what we would like for an n-dimensional array, and specifically, what would we like to specify the dimension of the n-dimensional array? In terms of expressivity, we would like something very concise, where you could specify in a concise way the dimensions that are fixed, the dimensions that are dynamic in arbitrary orders, and everything would be easy to read, easy to write, and easy to understand. In terms of performance, we are looking for something that will have no overhead compared to handcrafted solution that would be optimized and designed for specific scenarios. It exists. Some libraries exist for multidimensional arrays of rank 2, of rank 1, of rank 3. Here we want to maintain the highest possible level of performance, regardless of the rank of the n-dimensional array. And in terms of generosity, we like to have arbitrary memory layouts, arbitrary indexing schemes, arbitrary finite ranks from 1 to a lot, combinations of static and dynamic dimensions, and zero-sized case. So the challenge is to find a way to have all these things at the same time, expressivity, performance, and generosity. That is what the SAR library is looking for. Thankfully, we now have C++20. And when people doing a lot of template programming realized what C++20 was giving to them, they probably saw something like this. I know people who saw something like this. And in the meantime, they were like, hey, did anyone notice how this could go wrong? And I must admit that I was one of these people. Because C++20 is bringing something that is highly useful to do the kind of thing I described before. It basically brings an atomic weapon to do that. And this is the content of the proposal P0732, which brings in class types in non-type template parameters. Before C++20, it was only possible to provide integers or pointers or arrays, I think, as template parameters. In C++20, minus some restrictions, it will be possible to provide arbitrary objects as a template parameter. And this is extremely powerful. I see no question for that part, so I will just go to the next one, where I will describe how we can actually achieve a concise way to specify the dimensions of arrays. EDSL stands for Embedded Domain Specific Language. And this is basically the key. We will define a language within C++ to a language specifically designed to specify dimensions of arrays and shapes of arrays. What if I told you that the following was perfectly possible in C++20? So this is very close to some of the interface, to some of the expressivity example we have seen before. And this is actually possible thanks to C++20. So in the first one, we specify n-dimensional array of type double, and then we specify the shape. And it's compact, it's easy to read. We have fixed dimension, and we have combination of fixed dimension and dynamic dimension. Or we could even think of different way of specifying things, for example, with this contents version, where we have the template parameter of the contents that is the element type, and again, the shape of the array. And this is perfectly, as I said before, this is perfectly possible in C++20. So if we want to achieve that, one way of approaching the problem is to reverse engineer what we want to achieve. So when we see that shape cannot be a type, because a type, there is no way of calling the subscript operator on a type. So shape has to be a variable. Therefore, empty array should be a class template of the form class auto. Shape should be a variable of a type with operator parenthesis and operator subscript. And these operators should return a value of the same type as shape, so that it can be called again recursively until all dimensions are specified. And for the contents version, same thing, except this time, contents cannot be a type. It has to be a variable template, not a variable, but the variable template. In that form, and the array should be of the form template auto. Contents should be a variable of type with the true operators, and same thing as before. And if we have that, then we have the short syntax we are looking for. And this is where we introduce expression template. Expression template is the way templates wizards used to optimize linear algebra operations in C++. But now that we can pass any kind of object into as template parameters, it's possible to inject templates, to inject expression templates as templates. For the case we are looking for, shape will build an expression template, and the result of the expression template will be then injected as a template parameter. And doing that takes embedded domain specific language to a whole new level. So how to do that? The first thing to do is to create two markers, two tags to process the operators that are being called on shape. One for the function call operator, one for the subscripting operator. Nothing surprising here. The args will be used to specify how many arguments these operators are taking. Then we have the shaper class template. The role of the shaper is to be the type of the shape, since shape is a variable. So it's a class template that will have all the preceding operations as the template parameter. So it has a constructor that takes the preceding, that takes a shaper and a new possible index to be built recursively. And it has some data parameter. Nothing surprising so far. However, it has two operators, as we said before, one operator to build dynamic dimension and one operator to build static dimension. So the operator parenthesis will build a different shaper, adding the tag function call operator at the end of the operators that have been processed before. We also may want to provide a way to specify a default size for dynamic dimensions. And so therefore the operator parenthesis may take a parameter to specify that. And then the subscripting operator would do the same. It would build another shaper from the existing shaper. Then we have a way to access the rank, the number of already existing dimension, a way to query the parameter at a given position, and a way to convert the parameters that have been already passed to an array, and to build an array from another array, basically. The most important part in that slide is the fact that we have two main operators, parenthesis and subscript, and they build a shaper adding the tag of the next operation to come. And then we declare a shape instance of type shaper. And we declare indexing helper to help with constant time indices. So the type of the index is an index constant, and then index is just a variable template of type index constant. That's it. Then we want to have a dynamic way of specifying extent and a static way of specifying extent. So the first thing to come is an indexed dynamic extent. So we have two versions of it. We have a version with no default dimension, and we have a version that takes a defaulted dimension as a parameter. And these extents are indexed by their rank. And they have an operator subscript taking the rank as a variable. We have the same thing for static extent, except the static extent always take a value, the value at compile time. And then we build a class, a helper to build the things from the indices. So we specialize this indexed extent maker so that for a function call operator, it corresponds to an indexed dynamic extent. For a function call operator with one parameter, it corresponds to an indexed dynamic extent with a default dimension. And for a substituting operator, it corresponds to the indexed static extent. And then we have an alias to make that thing works better and works nicely, called make indexed extent. From that, we built an extent policy that will specify whether dimensions of a certain rank are dynamic or static. So the extent policy, the thing to see here is that the extent policy inherits from the extent. The extent being the indexed extent that associate the dynamic or static status with the rank of the extent. And we create helper to help building these things, and especially a make extent policy that takes that basically will convert a shape into a sequence of classes that could be then injected and inherited from the extent policy. Then we have the notion of an extender to specify at runtime how a dimension will be resized. So an extender, so we have this concept of indexed extender that will take an index as an input, and that will, as a template parameter, and that will take a size so that the dimension along a particular rank will be resized with a given number. And then we have extenders so that we can resize several dimensions at the same time. An extender is just a group of indexed extent. Nothing very fancy here. The extenders, in the same way extent inherits from individual extent, extenders inherit from indexed extent. And finally, we have our basic ND array with our extend policy. And because some dimensions have to be specified when the object is built, then a basic ND array takes a list of extenders at runtime. And this is, of course, this basic ND array could have a lot of different functions, but here, this is the most basic example. And if we have all of that, then by combining all these things together, we may write something like this, where we have an ND array of shape 3, dynamic 4, dynamic with initialized at 2, and a static dimension of 3. Constructed by specifying that the extent along the dimension of rank 1 is initialized at 5. So in total, we have along dimension 0, we have a static size of 3. Along dimension 5, we have a dynamic size with initial value is given in the constructor using the extend mechanism. A static size of 4, a dynamic size, dimension 3 is a dynamic size with the default initial value of 2, and dimension 4 is a static size of 3. So one of the questions is what's a default size for dynamic extent? Why we can just use -1 for dynamic extent. So the dynamic extent, currently dynamic extent exists in the standard as of C++20, and it's equal to -1. The problem with that is that it limits, it gives no way of specifying a dynamic default dimension, and as we'll see after, it will be it's kind of limited. And from the type system's perspective, using a special number for default case in something that is really template heavy is a bad idea. So given the time, I will skip the next part, and I will summarize the next part basically by saying that handling, because extents, the problem with extents is that because when all dimensions are static, extent can just be an integer sequence, and it works nicely. When it's dynamic only, then extents can just be a runtime array that stores the different extents given at runtime. But when when both are mixed, then it becomes complicated if we want to optimize it. Especially if we want to optimize the memory footprint so that only the dynamic dimensions are stored. If we want to optimize runtime access along a particular dimension, and if we want to optimize compilation time. And for people interested in all these aspects, I will leave the slide on the GitHub of the conference. This is quite technical, but it's possible to achieve these goals so that the memory footprint is really low. We have perfect runtime access, even with alternative dimensions. But doing it is way more tricky than one may think. So if the problem of extents is solved, then what's interesting is how what has been proposed in that talk could be extended. So because it's an embedded domain-specific language, expression template could be used to pass additional parameters, additional layout information. For example, operators could be used to specify some kind of layout information. Symmetries along one particular dimension could be expressed as a part of the domain-specific language. The parallelization information, for example, if we want to distribute the array along the first dimension, and if we want to vectorize it on the last one, or if we want to vectorize it and send it on the GPU on the last one, it would be possible to design a language using the same principle for an axis-based parallelization information. And doing that would make would be a very powerful way and concise way of specifying very complicated things. And finally, operation on shapes could also be possible. All of that are just thoughts, but all of that is possible. Also, there is currently a proposal to specify multi-dimensional subscript operator. If we had that, we could, including a zero-parameter operator, a zero-parameter subscript operator, it could bring other opportunities to enrich the language and to have the parenthesis and the subscript operator useful for different purposes with different meanings. Also, I talked about static extents and dynamic extents, and dynamic extent with a default dimension. But I think it would be worth investigating what could be the more generic concept for an extent. And I think a way to do that could be to divide, a suggestion would be to divide an extent between the following parameters. So a component that would be a static size under which the size couldn't shrink. An initial size at construction, basically bringing when you build an object, that size, when you build an object without specifying the size over a particular dimension, then the initial size will be taken. A threshold to specify how many elements can be stored on the stack and when the allocator is triggered, and a maximum number of elements that could be specified at compile time, the thing can grow to. And this could be infinite. In terms of these four parameters, for example, a static extent is just an extent where the four parameters are equal. A dynamic extent is an extent where the minimum is set to 0, the maximum is set to infinity, the initial and threshold are set to 0, so that as soon as one element is added, all the thing is allocated, the allocator is called, and everything is on the heap. And a fixed extent, where in that case the initial size would be 0, max element would be n, and the threshold would be n. So that's another thing we could think of if we want to generalize and to go beyond what has been presented. More generally, the generic MTTPs, I think, really open the Pandora's box. Because being able to inject objects as template parameters in C++20 is a game changer to design language. And now, template classes really are mini compilers. It would be totally possible, and that's what I showed in that presentation, is that it's totally possible to use a template class and inject a million language with its own grammar inside it. The next step to come, I think, to take it one level further, is the genericity regarding kinds. Because for now, and that has been proposed by P1985, because for now it's impossible to have something that could be a type or a value. The developer has to specify what the template parameter will be. It can be a generic value thanks to auto, but it cannot be a type or a value. P1985 proposed to standardize a way to specify something that could basically be anything, a value, a type, a template. And if this is brought to the C++, this will really make the design of a DSL and mini language far easier for template developers. So the conclusion for this talk is that, as I said in the introduction, linear algebra is everywhere. It's very complex when we try to balance between genericity, performance, and expressivity. And that is why it's very complex to do in C++. There is an existing effort being done with MDSpan. However, currently, the way to specify the shape of arrays requires a lot of characters. C++20 with arbitrary non-type template parameters allows to design embedded domain-specific language to specify multidimensional shapes in a much more concise manner. With that, it's possible to use what I call expression template to inject the expression template inside as a template parameter. And using that, it's possible to create what I showed before, which is, I think, far more powerful than just trying to relax incomplete multidimensional array type declaration, or trying to use -1 as a parameter. Because this could be used to specify, as I showed, where to parallelize, like where to do things along certain dimensions. Mixing dynamic and static extents are particularly tricky to implement. There is a trick to do that, which I call the log tuple trick, and people interested in that, which is a very useful pattern, can look at the presentation. As I said, extending the DSL can go in many directions, bringing layout information, symmetries, parallelization, shape operation. All of that could be brought into the small language I described. If we want to go further, I think an interesting direction could be to conceptify the concept of an extent, and so that we have a unique way of specifying when things are static, when things are dynamic, when things are resizable up to a certain dimension, when things are resizable regardless of the maximum, when things are not resizable under a certain dimension, etc. C++20 really is bringing something very interesting to EDSL design. And I think C++23, if kind genericity is allowed in C++23, it will take it even further. Thank you for your attention. I know there has been a lot of material, but if you have questions, I will read them. And I want to thank especially Joël Falcou because we are collaborating on the topic, and I think something very nice will write something very nice to handle these kind of things. So one question is, what do you think could be an interface to compare shapes of different arrays for compatibility or particular operation? So that's a good question. I didn't investigate yet that particular question because I wanted, my main purpose doing what I did was to show proof of concept, to show that it was possible to do that. And it is possible to do what I had in mind. Now that we know it's possible, there will be the question of how to do that in a nice way. And for now, I don't know. Do you think, question 2, do you think that dynamic static extents mix can be separated into something more generally useful, like partially static array? Yes, and that's for people who are interested in that. I would look at the part that I didn't have time to show about the extents. But yes, that's a way of doing it. But there are ways of doing that that are nicer and that scale better than a partially static array. And so if you have other questions, I can take a question offline in the track. There is a question 3, which is, what timeline do you envision for getting stuff like this into the standard? No, I would hope, the question being no earlier than C++ 26. I think actually this could be included in a revision of MDSpan, at least the most basic version. Because once MDSpan is shipped, I think it will cause later incompatibility problems. I think this is something that I want to look at with the author of MDSpan, but I'm hoping for a reduced version of it, just to specify static and dynamic version. I think this could be shipped in C++ 23, I hope. Thank you for your attention. And if you have questions, I will take them offline.